Welcome to Chapter 9, the sixth screencast for gases. In the previous screencast, we considered the factors that affect speed of molecules of a gas and talked about that a little bit. Now we're ready to look at the relationship between these factors mathematically. And these factors are related by the equation shown above. And in this equation, U stands for speed or velocity. We sometimes use U instead of V as the symbol for speed or velocity. So this is the average speed of the molecules. And it's a particular kind of average speed that you may or may not have heard about before. It's called the RMS speed. And that is an average where the average is done by taking the root mean square average. So we square the speeds and then average them and square root. So it's just a slightly different way of doing the speed or doing an average than you may normally be used to. In this equation, R, of course, is the gas constant. And as we'll see, we'll do it in somewhat different units than we have before to make agreement between the units of T, which is temperature, which, as you might suspect, must be done in Kelvin, and M is the mass, molar mass, of the gas particles that we are dealing with. And soon we will use this equation in calculations, but next let's talk about the relationship on a molecular level just a little bit more. So if we look a little more deeply at gas behavior via the kinetic molecular theory, and we look at the effect of factor 1, which was, of course, temperature, the effect of temperature on speed of the gas molecules, well, if the temperature is higher, the gas molecules are traveling faster on average. If the temperature is lower, then the molecules are traveling slower on average. And the effect that that has on, for example, pressure, if we have a constant volume of container, then if the gas molecules are traveling faster, they are going to hit the walls of the container more often and with more force. And those factors both, or those changes, both increase the pressure of the gas in the container. And of course, if the molecules are traveling slower on average because the temperature is lower, then they'll hit the walls of the container with less force and less frequently, and that's a lower pressure. So we can explain pressure in terms of, or how it changes with respect to temperature in terms of the kinetic molecular theory. We can consider the second factor as well, which was molar mass, and the heavier particles will travel at slower speeds, the lighter particles will travel at higher speeds, presuming, of course, we're dealing with the same temperature for both. And this can be heard, in fact, if somebody breathes in gas that is less massive than air, for example, helium gas, the pitch of their voice changes. It goes up quite a bit because helium molecules at the same temperature as air molecules will travel at a much higher speed, and that makes sounds that are created within that gas have a much higher pitch. And of course, if somebody were to breathe in some heavier gas than air, higher molar mass gas, then the sounds that they make would have a lower pitch because the molecules on average are traveling slower. If we change the volume of a gas, well, here's a container with gas molecules moving around, hitting the walls of the container with certain force, certain frequency, and exerting a certain pressure. And if we don't change the temperature but do decrease the volume, then the gas molecules, even though they're not traveling at any different speed and they don't have any different kinetic energy, will hit the walls of the container more frequently, and that will increase the pressure due to the more frequent collisions. And of course, if we made the container larger, then the reverse would be the case. we'd have less frequent collisions and a lower pressure. And we can also use the kinetic molecular theory to explain Dalton's Law. If we have more than one gas in a container, all of the gas molecules are going to be exerting pressure due to the force and frequency of their collisions. All of the gas molecules will occupy the entire container, and so the volume will be the same for all gases, and they're all at the same temperature. And so basically the pressure is just simply due to the pressure of one gas molecules hitting the sides of the container, walls of the container, and the other gas molecules hitting the walls of the container, all added up. Now, a new idea is when we have two gases, and here we have them in separate containers, they're kept apart from each other, and if we open up a little hole in between the two containers, what will happen is the gases will diffuse into or through each other. So if we open up a little hole in the wall between the two containers, we'd expect red gas molecules to make their way into the right side container and green gas molecules to make their way into the left side container. And this diffusion process would continue until there's an even mixing of gas molecules throughout. So the concentration of gas molecules on this side and on that side would be the same. As you might suspect, the higher the temperature of the gas and or the higher the speed of the gas molecules, the faster they're going to diffuse from one side to another. Now we sometimes, instead of dealing with diffusion, deal with something slightly different, in which case we have gas molecules in a container, and when we open up the little pinhole in between the container that has the gas molecules in it and the other side doesn't have gas in it at all, it's a vacuum. And the escape of one gas through a tiny hole into a vacuum is called effusion, not diffusion. And what happens is when we make that opening, the gas molecules effuse through, and they'll do that until the pressure throughout is the same. So we don't really have a different concentration, and we have equal pressure throughout. Again, the speed of effusion, rate of effusion, is going to depend upon the speed of the gas molecules, which in turn will depend upon the temperature they're at and the mass of the gas molecules. Now, we can use this to determine some things. For example, if we know, we do know that the root mean square speed of a given gas is given by this relationship, equals 3 RT over m, the square root. And if we consider having two gases, then gas 1 would have its root mean square speed equal to 3 RT over the mass of its molecules, and gas 2 would have its root mean square speed equal to 3 RT over the mass of its molecules. And this is an equation, this is an equation, and we can divide an equation by an equation, and we still have an equation. And if we do this, the 3 and the r, of course, will cancel out because they're the same. And if we do this at the same temperature for both gases, which we often do, then temperature cancels out. And so what we have is a ratio, that's kind of a funny way to do that. We have a ratio of the speed of gas 1 to the speed of gas 2 is equal to, and what's going to reduce out of here is we'll have the square root of 1 over m1 over 1 over m2. Everything else cancels out. And if we now simplify this a little bit, we get that the rate of effusion of gas 1 compared to the rate of effusion of gas 2 equals the square root of the mass of gas 2 over the mass of gas 1. And note, rate of effusion here is going to be determined by speed of gas 1. So the root mean square speed of gas 1, rate of effusion gas 2 will be determined by the root mean square speed of gas 2. So let's use this in a problem to determine an identity of a gas from effusion data, and we're going to get that via molar mass. So suppose we have oxygen gas effusing at a rate 1.62 times more than some noble gas. Well, what we know then is the noble gas is going to be heavier than the oxygen gas because it effuses at a slower speed. And we also know that the rate of effusion of one gas compared to another is equal to the square root of the ratio of their molar masses, but inverse. And in this case, let's call oxygen gas gas 1, and the noble gas we're trying to find gas 2. And so the rate of effusion of oxygen, gas 1, is 1.62 times the rate of effusion of the noble gas, gas 2. So we have 1.62 over 1. That's the ratio of their rates of effusion. Note, we don't know the speed of either gas, but we know that the oxygen is 1.62 times more than the noble gas. Oxygen, of course, has a molar mass of 32 grams per mole. M2 is to be determined. And since we know everything but the M2, we can use normal algebraic techniques to solve this. We want to get rid of the square root by squaring both sides. And then 1.62 squared is about 2.624. The square root sign is gone. And now we multiply both sides by 32. And that gives us 2.624 times 32 grams per mole is equal to M2. And therefore the molar mass of the unknown noble gas is 84 grams per mole. And if you look on a periodic table, we'll see that that is the noble gas krypton.